You know, it's kind of funny. You can hear literally two notes of a song, and your brain just instantly knows what it is. But one of the world's most powerful AIs can get totally confused by a slightly blurry picture. Well, we're about to dive into a breakthrough that's finally closing that gap. And it all comes down to rethinking one very basic thing: memory.
I mean, really, this is the whole thing right here. You hear that opening riff, and boom, your brain is already playing the chorus. But an AI, even a really smart one, can be completely thrown off by a tiny distortion in a photo it's supposedly seen a million times. This huge difference really puts a spotlight on a fundamental weakness in how we've been building machines to remember things.
So here's the core of it. Our memory is, well, it's flexible. It works with context. We see a grainy old photo and we know, oh, that's my friend from college. But traditional AI memory, it's rigid. Think of it like a computer's file system. It's looking for an exact file name and exact address. It only has one single inflexible way of measuring if two things are similar, and that, it turns out, is its biggest downfall.
Okay, so to really get what's so cool about this new approach, we first have to understand the specific kind of memory AI is trying to copy from us, and why the old way of doing it was, frankly, built on some pretty shaky ground.
The whole concept is called associative memory. The idea is, instead of pulling up a file using its exact name, you pull it up using a piece of what's inside it. You give the system a little fragment of the puzzle, a partial clue, maybe a noisy one, and it's supposed to find the whole picture. It's AI's best shot at mimicking that incredible recall we all have, but for decades, it's been pretty much stuck. And this brings us to the heart of the problem, what the researchers who wrote this paper call the proximity trap. It's a really subtle but absolutely critical flaw that has held back every single associative model, until now. For a long time, the rule was just dead simple. To find the right memory, all you had to do was find the one that was geometrically closest to your query in some kind of data space. So if a blurry photo is your query, just find the stored photo with the most pixels that look kind of the same. And look, on the surface that sounds perfectly logical, right? But it's a trap. This quote from the paper just perfectly exposes the flaw. It's brilliant. Think about the word click. Is it closest to tap because they mean similar things, or is it closer to clique because they sound alike? Or maybe clock because they're spelled almost the same? The point is, a single fixed definition of closeness just can't work. The right answer depends completely on the context you're asking in. So here's the formal definition of this trap. The old models were basically happy if they found any valid memory nearby. They might find the word clock when you were actually thinking about sounds. The system would check a box, call it a success, but it wasn't the right match for what you were looking for. And this really shows the problem. Just being close by doesn't guarantee you're correct. So, okay, how do you get out of a trap like that? Well, these researchers proposed a total shift in thinking. This is the moment AI memory stopped being just a filing cabinet and started becoming more like a detective. It's not about distance anymore, it's about figuring out the origin. And this is the big idea. A query, like that blurry photo or that snippet of a song, it isn't just randomly floating around in data space near the original. No, it was actually generated from the original. It's a distorted version, a variant of the real memory. And that reframes the whole goal. Instead of asking which memory is closest, the system now asks a much smarter question. Okay, given this distorted query I have, which of my stored memories was its most probable source? You see? It changes the whole problem, from one of simple geometry to one of probability. So, what do these variants actually look like? Well, the first type is what you'd call a noisy variant. Think of this like static on a radio, or a really grainy, low-light photo. The original information is all still there, but it's been kind of corrupted by random noise. That dark spot in the middle is the original memory, and that cloud around it represents all the possible noisy versions it could become. Next up, you've got a masked variant. This is all about missing information. The best example is someone wearing sunglasses. You can't see their eyes at all, but you can still totally recognize their face, right? Some parts of the data are just gone, completely hidden, but the rest is perfectly clear. And then there's a biased variant. This isn't random noise. It's a systematic change that affects the whole pattern. Think about changing the lighting in a room from a warm yellow to a cool blue, or just slapping an Instagram filter on a photo. Every single part of the image is altered, but it's all altered in a consistent way. And here's the reality check. Any real-world query, like a picture you took on a shaky phone in a dark room, is usually a messy combination of all three of these. It's noisy, parts of it are hidden by shadows, and the color is totally biased by a weird streetlight. This is the kind of complex mess that completely broke the old models. So if similarity isn't some fixed ruler you can use to measure things, what's the alternative? The solution, it turns out, is to build a new kind of mechanism, one that can actually learn what similar means depending on the situation. And this is it, the Adaptive Hopfield Network, or AHOP for short. Here's the simple version of how it works. First, it doesn't just calculate one lazy similarity score. It analyzes the query and creates this super detailed similarity footprint. Think of it like a detective's profile noting every single clue about how that query might relate to each memory it has stored. Second, and this is the absolute genius part, it applies adaptive weights. It learns which clues are important for this specific situation. If it's a masked photo, it learns to ignore the missing parts. If it's a biased one, it learns to account for that consistent shift. And finally, it uses those smart, learned weights to calculate a final, context-aware similarity score and find the true match.
Okay, that all sounds really great in theory, but, does it actually work in the real world? Let's take a look at the results when they put AOHAP head-to-head with other models in some seriously tough situations. Man, this really tells you everything you need to know. That big green area shows AHOP's accuracy. As you move across the bottom and up the side, the data gets messier and more distorted. Now just look at what happens to the other models, the ones in red and blue. They just collapse. Their accuracy plummets towards zero. But AHOP's green zone stays incredibly strong, holding on to high accuracy even when things get really, really messy.
Let's put some hard numbers to that performance. On a really difficult task, trying to recognize handwritten numbers, a modern model called mHop gets about 66% right. Another advanced one, khop, drops to just over 52%, basically a coin flip. But AHOP, it nails almost 85% accuracy. I mean, that's not just a little bit better. That is a massive leap in performance right where it counts the most.
So what's the big takeaway from all this? Well, this breakthrough gives us an AI with a much more robust, much more human-like memory. That leads to way better, more reliable performance on all those complex tasks that have to deal with the messy, ambiguous data of the real world. It's a huge step toward an AI that doesn't just calculate, but can actually start to understand context and nuance. And it provides a powerful new tool that can be plugged into all sorts of modern AI systems.
And that leaves us with this really fascinating final thought. We've cracked the problem of context-aware similarity in memory. So what's next? What other fundamental parts of how we think, things like analogy, creativity, or even just plain old common sense, can we now start to tackle by teaching AI not just to calculate, but to learn what truly matters?